Hey guys, welcome to the third video on A-level physics electronics. And this time we're going to talk about negative feedback and the op-amp. And now negative feedback is basically a manipulation of a comparator circuit. The only difference being that the output device, that is the heater which we talked about in the previous video, is now also connected to the sensing device. So the whole thing is actually kind of really changed, right, to incorporate that one change, but in simple terms you can remember that. And the actual wording in the syllabus in reference to negative feedback in op-amp is that you gotta understand the effects of negative feedback on the gain of an op-amp. And the gain when you're using negative feedback actually becomes like 1. So basically no gain at all, and one wonders how the hell is it an amplifier any longer. It isn't doing any amplification, but it does serve other very important purposes. And how the gain comes to be 1 is something we will be investigating in this topic. So what happens with the op-amp in figure 31.12 is connected to a heater which warms the air around the thermistor. So the heater is basically the terminal output device which is gonna do the thing. And the op-amp senses when the room is cold and switches on the heater, right? Right? So that is what we studied in comparator. And if it were to say get lower, then eventually the voltage would drop and then there wouldn't be any current flow to the heater, and that is comparator. But there's going to be a bit of a difference between negative feedback and comparator. And the heater then warms the room, and this information is fed back to the thermistor, which then senses that the room is now warm enough and switches off the heater. Now that's kind of interesting, like why do we need any feedback sort of thing? Well, if it's at 15, if the threshold is at 15 and then it starts the heater, then the moment it becomes 16 it should stop working because the threshold has been in the opposite direction, and that's not what we want. We probably want it to heat it up a bit further, and so we set the value at which it will close, and for that we need a negative feedback process. So this process is known as feedback and keeps the room at a reasonably constant temperature, because if it were 15 and at 15 it sort of switches on, right? So it's gonna keep heating the room. That doesn't make sense. You're gonna get boiled unless you have a negative feedback that's saying it's warm enough now. Or if it's connected to an AC and after, and if the temperature is 30 or maybe it's 15, and that is the threshold for which the AC is going to start working, but then there isn't going to be another threshold and it's going to keep on cooling the room, but you want it to stop at a certain point. And that is where negative feedback comes into play, and our heater is there. So it's just like I said, comparator to heater and sensing device to heater obviously, and heater back to the sensing device. So it's kind of like a really complicated love triangle. So there are many examples of feedback, in homeostasis in the body. Let's just go with this. But electrical feedback is also important. So consider the circuit in figure 31.14, and in the circuit we in the input circuit, and you should draw all voltages relative to it, because that is just standard protocol. So we have to show Vin relative to the 0 volt line and V out as well. In this example, they seem to be of the same polarity because they're pointing in the same direction. So one question is, how does the op-amp behaves with this feedback loop? The potential V minus at the inverting input is always the same as V out because of the feedback loop. All of it is being fed back in. It stands to reason why they would be the same. So at the top, write it. V out or V in is always equal to V out. Now this is interesting because in the case of the comparator circuit, the voltage or the potential at V minus is constant as well. So if you draw similarities, it's going to be easier for you to remember the concepts. So suppose that at the start both V plus and V minus happen to be 0. So let's write 1, t is equal to 0, V plus is equal to 0, and V minus is 0. So that's when we just started everything up. We haven't given any input, but then we give the input and V plus suddenly becomes 0.1, which isn't that big, but you know, an op-amp is able to amplify small inputs by huge amounts. So V plus is basically equal to 0.1, and because V plus is basically just a V input, the V input is equal to 0.1 volt. The op-amp multiplies the potential difference between V plus and V minus by the open loop voltage to produce V out. So interesting, right? So difference will be 0.1 and it's gonna be multiplied by G naught. So V out is at that moment is gonna be equal to the product of G naught, that is the open loop voltage gain, and the difference between V plus and V minus, and because V minus is 0, so it's gonna be 0.1, and because it's gonna be multiplied by G naught, soon it's gonna get a really huge value because that's like 10 to the power 5 into 0.1, so it's gonna be huge. So it's basically like 1 in 10 to the power 4 volts. Actually, it's not gonna be that big. It's just gonna be equal to the supply voltage, but just bear with me at the moment. Because the gain is very high, G naught being like 10 to the power 5, the value of V out increases rapidly. You can write that. Due to G naught being so high, V naught, or actually V out, rises rapidly. So what does V out become? You must remember that the output voltage is being fed back to the inverting. And we know that V out is equal to G naught into V plus minus V minus, where G naught is the open loop voltage gain. We know that. But just to reinforce this idea, I suggest you write the formula down. because we're gonna get to some really heavy stuff here, right? And since V out is equal to V minus, we just established that, and V in is equal to V plus, we also established that. We have V out is equal to G naught into V in minus V out. So we multiply both V in by V out, V in and V out by G naught. So we get V out is equal to G naught V in minus G naught V out. And so we take all of the species that have V out onto one side, so it becomes V out plus G naught V out being equivalent to G naught V in. And then what do? We take V out to be common, so it becomes V out bracket 1 plus G naught, and that's like equivalent to G naught V in. And because what we were actually investigating in the first place what was it that we were investigating? We were investigating the change in G naught. So if this is true, if V out is equal to V minus and V in is equal to V plus, then what is the value of G naught? How do we do that? So what is the value of the actual gain? We are talking about the gain and we're not talking about the open loop voltage gain. So what's going to be the gain? We know the gain is V out over V in. So let's manipulate this in a manner so we get V out over V in. So we get V out over V in, and when we do that we have to bring 1 plus G naught onto the other side, so it becomes V out over V in, which is basically the gain, is equal to G naught over 1 plus G naught. And because the open loop voltage gain has such a high value, 1 doesn't have a lot of effect on it, and so basically it's equivalent to 1. And so it's the actual gain which is equal to this and not G naught. G naught is still going to be 10 to the power 5 because that is a constant for a particular op amp. So the actual gain when it's like this is going to be 1. We can also figure it out by using V out over V in values. It's going to come out as 1. So there are certain components with high internal resistance, such as a piezoelectric microphone, which is actually also a sensing device. I might talk about this in another video. And because of that high internal resistance, at the output of it, there isn't going to be a lot of current. So if we connect the output of the piezoelectric microphone with the input of the op-amp, then from the output of the op-amp, we're going to get the same voltage because of there being like zero internal resistance, so there isn't going to be any drop, but we're going to get a larger current, and that can be used to operate some other component which wouldn't have been able to operate if it were directly in series with the high internal resistance piezoelectric microphone. This is interesting. So if they ask you like, why do we have this, like why do you want that, why do you want to have a G0 of 1, it's not going to do any amplification. In a comparative circuit, there was amplification observed, but it wasn't exactly what we were looking for, were we? That was just a byproduct of it. And the byproduct was what was allowing us to use it the way we wanted to. So what does it do? Acts as a buffer between electronic circuits. What else does it do? Operation of another component in series with the component of extremely high internal resistance. And why is it suitable for this? Because if it's like zero internal resistance, it won't use up any of the current, it won't use up any of the voltage. And that's also the reason we are able to use it in a potential divider circuit, and also why we can use it over here, and also because a lot of current will get out even though none is going to get in. That has to do with amplification. With the component with extremely high internal resistance. What else is the advantage? The frequency of the input signal does not affect the gain. We do know the concept of bandwidth because op-amps tend to have a finite bandwidth, that is a small range of frequencies whose amplitude will be amplified by the same amount, and for the rest of them the amplification won't be equal, so the signal would be distorted, won't be reproduced exactly. But for this, the bandwidth is gonna be bigger. So frequency does not impact amplification or does not impact gain. So effectively we have a larger bandwidth.